Hi all, this is Mr. Yeager with physics. What we're looking at today is we're going to do a quick simulation using the website PhET from the University of Colorado to kind of illustrate the brightness of light bulbs in series versus parallel. And then I'm going to do one more quick circuit problem so you can continue to try to figure out those complex circuit problems, which I know are tough. So what you see here is I've created a series circuit. I have one whole loop. Currently it's not on. The little blue dots represent the electrons moving. I have a battery, a light bulb, and a switch. Right now I would say the switch is open, which means that the circuit is off. When I close it, boom, circuit is on, circuit is closed, and now the light bulb is nice and bright there. Okay? So one of the concepts we want to try to quickly show, again going back, this would be open, closed, open, closed, open, closed. Alright, so anyway, one of the things we want to show is what will happen to the brightness of the bulbs if I continue to add more light bulbs to a series circuit. We talked about it, it should dim. So I'm going to break the wire, which again shuts everything off in a series circuit. I'm going to add a new light bulb. Turn it this way. Alright, and now connect it, and boom, now I have two light bulbs on. You can see it's definitely a bit more dim. If I add a third light bulb, it's even more dim. That's because, again, they have to keep on splitting that voltage. All right, they all share the same current, but they're splitting the voltage into smaller and smaller fractions, which produces less and less power. Brightness depends on power. Okay? All right, so now I have a parallel circuit. Right now, actually, it's still series. It's only going around one loop. But now, if I'm about to connect this top part here with another light bulb, we're going to see whether it should change the brightness of the bulb. So if I add another one in parallel, it should not change the brightness. The first bulb did not change, and the second one matched it perfectly. This is because they share the same voltage. The total voltage goes through both. You might sit there and go, well, doesn't the current decrease? It actually doesn't. What happens is the overall resistance actually decreases when you go into parallel because you do the reciprocals. And so the current actually will increase proportionally and therefore give them basically the same amount of power overall. All right, so that's kind of showing you the quick example there. I'll disconnect it. You can see the other one continues to run. That's the nice thing about parallel circuits. You can disconnect one wire and the other keeps going, and the brightness does not change at all. All right, so moving on from that, we're going to head on over and look at this complex circuit. All right, so you can see here, this one's similar to the one we did on the prior video. All right, it's definitely complex in terms that you have the parallel, but you can see I've added another wrinkle to it. I have a series within the parallel, and then you have the one R4 sitting outside of the parallel circuit. So once again, we're going to try to solve for a lot of different pieces. If we're able to solve for everything, I can ask you any question on the test, and you should be able to eventually get to that particular answer. So there's a lot to solve for. We got total voltage, total current, total resistance. Then we have all the different voltages, V1, V2, V3, and V4. We have I1, I2, I3, and I4. And we have R1, R2, oh, a little bit high there, R2, R3, and R4. All right, so resistances are again given to us. So 2635, 2635, 2635, 2, 6, 3, and 5. Okay, 2635. Very good. All right, we're given those, but then we're also given this thing up here, this circle with an A. All right, what the heck is this? This is an ammeter. It's measuring current. It's telling you that, saying it's reading 15 amps. Now the important thing here is, where is it reading those 15 amps? It's reading it near the battery, outside the parallel circuit, which means, has the current split at all yet? The answer to that's no. So the total current in the circuit is 15 amps. It doesn't split. It's going to stay the same all the way through. Oops, sorry, wrong way. All right, those 15 amps are going to then enter the parallel circuit. That's where they're going to split. So this will not be 15 through here, through each side. But then they'll come back together at the other junction, which means R4 does actually receive all 15, keep going the wrong way, all 15 amps. So we do actually already know I4 as well. From there, I can immediately calculate the voltage through R4 because V equals IR, the only formula we're really using for any circuit problem. 15 times 5 is 75 volts. Okay, so we have 75 volts. So now, this is where people immediately get stuck. Okay, they're going, okay, what can I do next? What can I do? Okay, does that 75 volts, is that the same through all of these? No. This is pulling out 75 volts of the total voltage from the battery. So this is the total voltage, not 75 either. It's taking 75 of those volts. The parallel circuit is taking all the rest. But we need to figure out how. How is this parallel circuit taking out the rest of it? So that's then our next step. We have to condense this parallel component of the circuit. So the first thing I would do is I combine R1 and R2. They are in series with each other, which means resistors in series, I simply add the two resistors up. So 2 plus 6, basically I'm going to replace two resistors over here with quote-unquote a larger resistor, which I'll call R1 plus 2, and it's 8 ohms. 8 ohms being added right there. Okay, 2 plus 6, right? Yes, okay? So now, the thing is, this still doesn't give me an answer. Now I can combine R12 with R3. They are parallel to each other. So R1, 2, 3 will equal the inverse of 1 over 8 plus 1 over 3. Inverse. Okay, sorry, get rid of that. Inverse. All right. So basically, I'm going to erase all this stuff and make one much larger resistor that's technically in series with R4. This is going to be R1, 2, and 3, and that'll equal 2.2 ohms. 2.2 ohms. That's how much resistance is in that whole section of parallel circuit. So if I add these two up, 2.2 plus 5, 2.2 plus 5, 7.2. That's my total resistance, 7.2 ohms. Okay? So now I know total current and total resistance, so I can multiply those two together. 7.2 times 15 is 108 volts. So that's the total voltage coming from the battery. So now, let's think about this. All right? How can I figure out how much is going into that parallel component? Well, if the total voltage is 108 volts from the battery, R4 is taking 75 of those volts, how much is left to go into the parallel component? So I subtract that. 108 minus 75, there's 33 volts going into, quote unquote, 1, 2, 3. The thing is, be very, 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 very careful here. Okay? The answer is not 33 for all three resistors. All right? We have to now go back to expanding it. There's two resistors, 1, 2, and 1 on the other side. All right? There's 33 volts going in here. So 33 volts does go down R3 side. That is going down R3. Okay? So R3, V3 would be 33 volts. It is receiving that much voltage. The thing is, this is where again lots of people get tricked. 2 ohms and 6 ohms. These are in series, so what are they going to do to the voltage? They're going to split it. Even though this side going into the voltage is the same in both branches, one resistor takes all the voltage, these two have to split it. Okay? So the thing is, I still need more information. All right? I need to basically figure out the current going into the other side. So I can figure that out. 33, all right, 33 divided by 3, there's 11 amps going down the right-hand side. All right, so if you think about it, 15 amps enters the junction, 11 amps go down the one side. How much is left to go down the left side? It would be 4 amps. And what do we do in series? Both objects receive the same current. So now I know I1 is 4 amps, I2 is 4 amps. Okay, I1 and I2 are both 4 amps. And then if I multiply 4 times 2, V1 is taking 8 volts, 4 times 6 is taking 24 volts, Again, what should these add up to? Technically 33, but because of rounding, it's going to be a little short. That's fine. That's fine. That's fine. That's fine. You're going to have to get over the fact that it's not going to always be absolutely perfect. You're going to be probably within 1 or 2 even sometimes, all right, depending on how you are rounding. That's fine. They should generally be close with V3, okay, is what we're looking at there. So that's, I mean, it's a big problem. It's tough to kind of figure out all those steps. Again, it's all about compressing this component first, using those series and parallel rules of what stays the same and what changes. All right, you can see how much I sometimes draw on it. Go ahead and draw on yours and go, okay, this is going one way. What's this going to go on the other side? What's going to be split? All right, and then you can answer pretty much any of the complex circuit problems I end up giving out to you. All right, so good luck.